So the data might come in a format that is really hard to process anyway. Also, the data might come into format that is somewhat redundant and doesn't really highlight what's important in the data. So the whole idea of data representation is to put data in a new format that is amenable for, that allows to do good processing, both from a optimization perspective and from a modeling perspective. So this is, of course, not the precise definition, it's just a rough intuition. Just to try to attach some symbols to what I just said, we're actually going to introduce basically what we introduced already, which is the idea of a feature map. A map that might be finite dimensional, might be infinite dimensional, and maps the data from the original space, what we called X so far, into a new space that I called F, the space of features. Of course, this definition, the only things that you might think that you get at the beginning is X. Both phi and F are part of the definition, okay? The space where you map things and the way you map them are part of the definition of what is a data representation. So just to guide you through the literature, what we called so far feature map is basically, is so general and is so unqualified, it's just a map from the data space into another space, that depending on the kind of features you require in this map, you might find this concept in different fields. And so if you read about analysis operators or transforms in signal processing, or an encoder information theory, an embedding when you talk a bit more about geometry, they're all mapped from some data space into a new representation space where you hope to preserve or capture some of the properties of your data. So one thing which is debatable is, suppose that you want to learn a representation. So far, what has been the feature of everything we discuss is that all the algorithms we consider started from a given representation, either a linear model or a model written on a dictionary of features, or a one given by a kernel. But the linear model, the features, or the kernel were assumed to be given. So the question here is, can we learn it? Can we learn it in some way? And now, it's debatable whether this process should or not be supervised. Because on the one hand, if you have labels, it's pretty clear what's your goal. You want a representation which is good to make prediction better, to solve your supervised problem in a better way. On the other hand, one idea is that labels might be hard to get in some cases, and in any case, they are the expensive process. If you just want to get images of faces, that's kind of easy, but if you want to get images of my face, your face, and so on, you need somebody to sit down and annotate the data. So the annotation, the getting the labels, is the hard part, typically. And so if you look into the literature, you've seen that people have been trying to push the idea of learning representation in an unsupervised way. Let me also say that here, I'm actually not going to take that much a top-down approach. I mean, we still don't have a clear understanding and a clear theory of what does it mean to learn a representation. So largely what I'm going to do is just going to present in a hopefully organized way some attempts that people have been doing. So I'm mostly going to record what they've been doing in a kind of compact notation. I'm not going to tell you that this is the best way of doing things. So many of the things we've discussed can be written one way or another like this. We want to learn a function, and we have something like this. And typically, we assume, so far, we assume these to be given, and we try to learn in a supervised fashion this guy. The idea here is that perhaps we can also learn this. And maybe we can try to do it in an unsupervised way. Now, this idea of cutting and saying, I want to learn this in an unsupervised way and in a supervised way, a little arbitrary, okay? Why does this make sense? Wouldn't it make sense to write these, also learn this supervised? Maybe. Wouldn't it make sense to try to be semi-supervised, or use both labeled and unlabeled data? Yes, okay? So this is just the first step, and again, it's just because I want to tell you about a bunch of techniques that somewhat forces this perspective. They say, well, I assume that first I get to know a lot of unlabeled data, and I don't exactly know which kind of questions people are what kind of labels they're gonna get later on. But I still try to get some reasonable features. And then later on, I get questions. I get labels that you can ask, you got labels that you can see as question you can ask about the data, and then you can specify better the representation you want, okay? So there is really this, we simplify the problem this way. So imagine that this is the part where you learn, you just have unlabeled data, but you don't know yet what kind of labels you're going to get. You don't know yet what kind of question you're going to get. And so a question you can start to put in your memory is, well, but if I don't know what kind of labels I'm going to get, how can I really write down a problem? What are kind of requests? What is a good data representation? It looks like a chicken and egg problem. A good data representation is the one that reduces the amount of labeled data you need, but actually you don't have the labeled data yet. So how do I know what's good, right? So let's postpone that a little bit. So we're going to assume that our data now, for the first time, they look like this. So it's the usual data sets, but with no labels, okay? And we still make the assumption that there is an underlying distribution. So I still call it rho, because I have nothing else for a while, but here rho is just the distribution over the inputs, okay? Because they don't have outputs. Now, if you ask yourself what could be principles, what could be a good representation in the absence of labels, what could you say? If you pick the next slide, shut up. So I just give you the data, and you don't know what kind of labels you're going to get later on. If you want, this means I give you, say, images, but I don't tell you what kind of question I'm going to ask about the image. Is this a face or not? Is there a tree or not? I'm not going to tell you this kind of question, but I just give you the images. Now you want to find the representation. You would like to write down a problem where you say, well, I have the data, I try to minimize this and that, or I try to enforce this and that. What is this and that? What is a good property of the data you might want to, what is some properties of the data you might try to preserve or enforce? No, you cannot. Mickey probably could do this class because he works on dictionary learning, so he cannot answer these questions. You could try to separate them in groups, you're saying? Yeah. Clustering, saying. Right. Okay, so let's split what you just said in two parts. One idea could be, well, I could try to separate them in groups. That's could be tricky because, yes, but it could be tricky, right? Because you don't know still which group. So you might have questions, depending on the way you project the data, you could see certain groups or other groups. But yes, it could be a first idea. Let's see if there are groups. The other thing he said, which you put them together, but it can actually be separated, is, well, let's try to learn a way to measure distances or similarity between points. Maybe because I already have clusters, or maybe because I do something else and I try to make sense of what does it mean to learn a distance. For example, one thing you could say is, when points are very far away, maybe I don't believe that they should be close, but when they're close enough, they should be close. So I try to say, give me a mapping that preserve distances when they're close, and maybe when they're far away, it push them apart, okay? This could be a reasonable thing, if you think in terms of similarity. What else? So this could be one idea, say, the idea of learning a metric. What else? The dimension should be low. Good. So if I take the data and I send them in the number 1, the dimension is really low, right? Is that enough? Right. So the idea is that On the one hand, you might want to try to get a parsimonious representation of your data, like a compact representation of your data, but clearly this requirement is trivial unless we put something else, which is we want to reconstruct the data in a decent way. We want to preserve the data in a decent way. Of course, this seems like a strong requirement, because why would you want to reconstruct the whole data? Well, remember that we don't know what kind of questions people are going to ask about the data. So the moment we decided we're going to throw away some stuff, this might be the stuff that is useful for later on information. So here the idea is more like the data are maybe complex, nonlinear, but they have some structure. They might be affected by noise. And what I want to get is a nice representation of the structure in the data in a compact way, perhaps getting rid of the noise. So we want to develop this idea. And here we just make it a bit more formal. So the first idea, to talk about this idea of reconstruction, we need to introduce what we mean by reconstruction. And so we need also, besides the feature map that maps the data in the feature space, we need something to get us back so that we can compare to the original data point. So we called a reconstruction a map that now is from the feature space back to the original space, so that now you can compose. This is just the composition. So you take the data, you represent them, you get a feature representation, then you go back, you're in the original space, and then you check how far you are. All right? We still haven't introduced the notion of the idea that this has to be compact. But this is what allows us to talk about reconstruction. The other idea, the one about similarity preservation, is the idea that here I'm sloppy, okay? I'm not sloppy, but I'm just being a bit general, not too precise. I say, if two things are similar when they're close, okay, you can think of this, if the distance is small enough, then I would like these two things to also be close in the feature space. This could be an idea, okay? And we see in the literature, this has been the two main ideas that guided the development of algorithms to learn data representation in an unsupervised fashion. So, turned out that somewhat the first idea has been developed much more than the second one, whereas the second one has been mostly developed in a kind of supervised setting, where you assume that somebody comes to you. I'm going to tell you later on a bit more about this, but the idea, oftentimes what people did is saying, well, I come to you with xi, xj, and then a label yij. So this is input 1, this is input 2, and now I tell you if they're similar. Say 1 if they're similar, and 0 if they're not similar. Okay? Up to the fact that this is more complicated, this is, a supervised learning problem, up to some renumbering. This is just a supervised learning problem where you have input and outputs. And so a lot of the things that have been done in metric learning are supervised. They essentially try to extend the ideas that you have in supervised learning to this more complex situation where you try to learn either a distance or something with less property than a distance that sometimes is called a similarity. But as it turns out, in some sense, most of the approaches here kind of uses the idea that some supervisor gives you the labels, whereas most of the supervised approaches have been focused mostly on the idea of looking at reconstruction. So that's what we want to discuss for a little bit. So the basic idea is, again, let me just remember how much I talk. The basic idea is that this is going to be our building block. The idea that we want to keep the information about the data. We want to be able to reconstruct the data. Now, if we try to now minimize something, the basic idea is very similar to what we did so far, meaning in practice, what you can do is to try to find a pair, reconstruction and representation. Notice that you need both, okay? While you're even only interested into the representation, you still need to look at the reconstruction to be able to describe anything. So in practice, you could look at something like this. This is a pretty obvious quantity. You just say, this is the reconstruction of the data I have. In the back of your mind, you might think that this is just a proxy to an ideal quantity, which is just the true reconstruction, the expected reconstruction where expectation is over all possible input points. The first time one sees this, if you're coming from supervised learning, you're quite happy, because you say, well, this smells like empirical risk, this smells like expected risk, maybe I can just click the overfitting, oversmoothing, regularization, prior, blah, blah button, and I can keep on going. Right? Usually the story is, I would like to minimize this, but in fact I don't have enough data, so I'm going to do this, but then I can overfit, so I'm going to regularize. As you will see in a second, we come up, well, that would be something very similar to regularization, but the reason is a bit different. If you remember what we did when we started from in the supervised setting, we got here, and then we said, well, let's try to see if there is a minimizer, and we introduced the target function. For the square loss, you remember what was the target function? What? The average, right? For each output, you fix the input and you take the average of all the output. It's called the regression function. And you can take the median, you can take the Bayes decision rule, and so on and so forth. But the main point is that those things, you could not compute the optimal, the minimizer of this, could not be computed. The minimizer of this functional here could not be computed. It depends on the probability distribution that you don't have. You don't have the conditional probability distribution. You cannot compute the median of the conditional distribution. Here, the situation is different. What is the minimizer of this? Can you give me a minimizer without looking at the data and without making any computation? Yeah. So somebody said identity. What does it mean? Give me any pair, psi and phi, that composed gives me the identity. For example, identity and identity. You just copy the data. Okay, you have the data, you copy them. You do nothing. Well, this, while you don't even have to look at the data to do this, you just have to check the dimension of the data, and this is going to be how much? 0. Okay, so while the setting seems very similar, there is a big difference. This problem has an obvious solution that you can find without looking at the data at all. So this makes a huge, it is a big divide, okay? There is no free lunch theorem, it's a free lunch. Here it is. Okay. It also says that we haven't defined the problem yet, in a way. It says that this problem is ill-posed, but not because we cannot find a solution, but because we have too many solutions, and until we say which of these solutions we want, we can always just solve it by picking up a trivial solution. Okay? There is always a trivial solution. So it makes sense once we put a prior and say, okay, but among all these solutions, we want the one that our friend up there said, the one, say, with small dimension. And maybe we're going to replace small dimension with some other assumption, which is like, among all the solutions, I want the one that is simple in some way. Okay? By doing that, we're going to end up with something that looks a lot like regularization. Okay? This is the roadmap. We start from a problem that does admit a trivial solution that avoids learning, but it might not be the solution we want. So it has multiple solutions, and among all those solutions, what we try to find is the one that satisfies some further criterion. If at the beginning I said that we want parsimonious reconstruction, we want a compact representation that preserves the information in the data. Here the information is just the reconstruction. We have to agree what we mean by parsimonious compact. We said low dimension, but maybe there is something else. Okay? So we begin by, what do we expect we need to do? We need to restrict the possible class of representation and reconstruction pairs that we allow. Okay? This is what we need to do, because we have to say that they have to be simple in some way. So we're going to begin doing this in a slightly abstract way, but you will see in a second that it becomes very natural. The first step we do, the one that's written there, is not really limiting. We have not really done much yet. We have not limited the class of representation or reconstruction yet. So let's see what's written here. We say that this map, psi, the one goes back from the coefficient space. So first of all, I'm always assuming that both the input and the feature space have linear structure. That you think of them as RD and RK, or a Hilbert space and a Hilbert space, okay? I'm always assuming that. And we assume that the map that goes back from the feature space to the data space is linear. So if you want, is a matrix in the simple case. And in a minute, it's going to become a dictionary. Then here we write this in this kind of fancy way, and we say that we call it the nearest neighbor representation, or nearest neighbor encoding. This is a term borrowed from information theory. The idea here is that given the reconstruction, we are going to try to find the coefficient that gives me the minimum distance to the original datum. But notice that here coefficients and this linear map belong to some set. The linear map belongs to some big set of matrices D, and the coefficient belongs to some set F lambda. So they might, in a minute, I'm going to put constraints. And I'm going to say, well, you don't take all possible coefficients and all possible matrix psi. You restrict yourself to some subset. So the matrix psi, as I told you, can just be seen as you can see it as a dictionary. Okay, just a collection of elements, a generalization of a basis, as we said a few times. So you can see the elements of this dictionary to be A1, AP. So when you apply, this is just psi beta. When you apply psi to beta, you just get AJ, BJ, where this is the size of the dictionary. Okay, this is just because it's a matrix, it's linear. So the psi becomes just a dictionary. That make sense? This thing here, if you want this, forget about what I wrote up there. If you just look at this thing, let's skip 1 second the reason why this is called nearest neighbor. If you look at this looks a lot like just standard regularization. Okay, where you say, minimize the squared error on a linear model subject to a constraint or adding a penalty. Here I'm not adding the penalty, I'm putting a constraint. But this looks like the usual thing, right? It's like, if you think of this as a signal, then I want to find given the dictionary. So this is for reconstruction, but usually we call this Y and this X, because we are in a supervised setting. Here we have that this is X, and this is some dictionary, but for now I assume it's given in this slide. And so given the dictionary and X, find the best coefficient that can reconstruct that X. And maybe put a constraint on the coefficient. Okay? We're still abstract, but the rest of the class is going to be 2, 3, 4 examples of essentially D and beta lambda. F lambda, sorry. So, again, instead of this, you could now consider something like this if you want. And this really looks like the stuff we've been discussing. There is some lambda hidden somewhere, and here, rather than constraining the coefficients, we take all possible coefficients, but we put a penalty. For the sake of simplicity, in most of this presentation, I consider this form, but you can think of this form if that's the one you digested more in the last few days. They're typically very related and in many cases equivalent. Okay, so we haven't made any big restriction yet, but we did assume that among all possible reconstruction pairs, we consider representation that are linear and reconstruction that, reconstruction that are linear and representation that are just made by this. And here I'm implicitly assuming that the constraints on the beta I are independent. So when I have to optimize over, so this is just the optimization over psi. When I have to optimize over the beta I can push it in the sum. If you now look at this equation, ignore this minimum here and this sum, and just look what you have here. This is the standard regularization to reconstruct a signal or estimate a signal from a given dictionary. You fix the dictionary, you now add the signal, and then you want to find the coefficient that best explains that signal, right? So if you fix psi, this is, the standard thing you do when you have a signal. You take some dictionary, say Fourier, wavelet, whatever you want, and then you just try to decompose the signal on that dictionary. But here, what we're saying is, well, I actually don't know the dictionary, and so I'm actually going to try to estimate the dictionary by minimizing the average reconstruction over a set of possible dictionaries. Okay? So, by assuming the psi to be linear, we can view it as a dictionary, and as we go on and optimize not only over the representation, but also over the reconstruction, you can interpret this as basically doing the usual estimation of the coefficients, but over a dictionary that now you don't know. You have to estimate. And so, if you were to alternate these two things, you're basically, the step is, given the dictionary, estimate the coefficients, then now, given that, estimate a new dictionary, and try to find out the best couple that give you the best reconstruction. You seem lost. I don't know if it's breakfast was heavy or sun was too strong yesterday afternoon. We are still abstract, right? We are still at the level where we say we do regularization, and I don't tell you what kind of regularization I do. I just say, I put some constraint here, I put some constraint here, now we're going to make example of constraints. And we'll see that this framework is large enough to encompass a big, big number of examples. Yep. So again, regularization is typically some constraint, either in the form of a penalty or in some other form. Here, D might not be the set of all possible matrices, can be some matrices. So that's, if you want, a first constraint. And here, beta belongs to not the whole set of coefficients, but some subset that I call f lambda. So that's the other constraint. So again, we have to agree what we mean by regularization. Again, here regularization is not that much a tool to avoid overfitting as much as a selection tool of the right solution. And this is encoded with this constraint and this constraint. Two choices, the constraint on the dictionaries and the constraint on the coefficients. And you can put both as penalties if you want, okay? And now I'm putting just them as constraints. Other questions? Okay, so now we are at the step where we said, I like reconstruction, but reconstruction doesn't give me a selection criterion for the solution. I put some extra constraint, and here is my general framework. Can we recover some useful algorithm by specifying f lambda and d? This is a partial list. So PCA, kernel PCA, sparse coding, k-means, an extension of k-means that is mixing things up with PCA called k-flats, and the list is long. Non-negative matrix factorization and tons of other matrix factorization problems can all be seen as take what I just showed you, choose f lambda, choose d, and just see what you get. Okay? So all these methods can be seen as reconstruct the data in a parsimonious way. And depending what you mean by parsimonious, then you get a different algorithm. Okay? I'm going to call all these methods, I'm going to review all these methods as a dictionary learning algorithm. PCA is typically seen as a dimensionality reduction under, if you want, a constraint that you can reconstruct well. And so this is not so surprising. Sparse coding is basically going to be an extension of sparsity, where you don't know the basis. K-means is typically seen as a clustering algorithm, so if you want, it goes a bit in the direction you were suggesting. But here we're going to review it from the perspective also called vector quantization. And again, we will see that it's just one specific choice of a dictionary and set of coefficients. So let's first begin with the PCA. We're going to get to the PCA you know in a minute, okay? But now I just write you the PCA from the perspective of a dictionary. And this is basically saying, we don't just want a dictionary, we want an orthonormal basis. That's it. That's basically PCA. If you write what I just wrote before, but I say, I don't want just a dictionary, I want an orthonormal basis, everything else essentially fixed, you get PCA. This is the way we say we want an orthonormal basis. We want a basis which is orthogonal to itself, okay? So it's an orthogonal matrix. Now, well, okay, I did it backward. So, you remember I have now to minimize both over psi and phi. But this is what becomes the minimization over phi, it's just the nearest neighbor encoding. So let's assume for a minute, for the sake of simplicity, no, in fact I didn't do it. Let's assume that psi is given, and it's an orthonormal basis, and let's minimize with respect to beta, all possible beta. What do we get? Well, you see it, you have to take twice psi transpose that apply to x minus psi beta. Did I wrote it? No. So if you minimize that, you get psi transpose x minus psi beta equals 0, with the 2 that I already take out. And what is this? So this is what gives you the representation, okay? Fix the dictionary, find the beta. Well, let's find the beta. The beta is equal to phi, boom, transpose psi beta equal psi transpose x. How much is this? Yes. How much is this? Just to check if somebody's awake, because I mean it's written up. This is the identity, so this goes away, so this is what you get. Okay? Let's plug it back in. You get x minus phi transpose x square. I think I denote the transpose by the star because as a joint, but it's the same. So now you look at this. This says if you give me a dictionary, the way because it's an orthonormal basis, the way I represent the dictionary is just by using this coefficient here. But now if you look at this, what is this? What is this operation here? If you have an orthogonal basis and you take, rather than psi transpose psi is the identity, it's written here. If you swap the order and you do psi transpose, what do you get? No, it's an orthogonal matrix, so it's a very special matrix. So you do get, he's saying you get the covariance. Yes, but it's a special one. Let's take one dimension, okay? If you take this and you take one dimension, so this is the general one, okay? If you take just one dimension, this is what you get. If you just take, so psi transpose is equal to this. It's easy to check. If you just work in one dimension, you just get this. And what is it? It's just a projection, okay? So psi transpose is the projection on the span of the element of the orthonormal basis. Okay, that's it. So you're given an orthonormal basis, you now project on the span of the orthonormal basis. Of course, you have two situations here, and I've been somewhat hiding one point, which is important. You see here, I'm assuming K to be less or equal than N and D, which means that I might take an orthonormal basis that span the whole space of coefficients, or I might take an orthonormal basis that is smaller, the span a space that is smaller than the whole set of coefficients. In that case, it's a proper projection in some lower dimensional space. So K here is exactly how many principal component, if you want, how many elements in the orthonormal basis you take. Okay? So we assume that we have an orthonormal basis spanning a subspace of dimension k. Assume you have it. Then you discover that the best thing you can do to get coefficient is just to project on that subspace and get those coefficients. This is what's written here. And then you still have to do the real part of the deal, which is to actually find these orthonormal bases. We haven't done it yet, right? So far, we just assume that it is given to us, and we just remember what happens when you have an orthonormal basis. But now you have to find it. So you still have to solve this minimization problem. Okay? So what does this say? It says, try to find the orthonormal basis, or if you want, a corresponding subspace of dimension k, so that when I project the data there, I get the best possible reconstruction of the data. Okay? This is what's written here. So from a modeling perspective, if you take dictionary learning and you assume that the dictionary is an orthonormal basis, you end up basically try to find an orthonormal basis that gives you the best reconstruction. That is a subspace that gives you the best reconstruction. So from a computational perspective, it's, I imagine more or less all of you know, you can massage this a little bit, and this just become an eigenvalue problem. You can find out that the best subspace, given a set of points, is going to be essentially the one spanned by the first k eigenvector of the covariance matrix of the input points. How many people are familiar with this? Everybody else is in the wrong place, because if you have not seen this in the first machine learning course you already taken, there's something wrong, okay? But it's 3 lines, okay? You know it, because you were in class. So in the notes I have, it's spelled out. Just if you just forget about the probabilistic perspective on PCA, just look at reconstruction and you just do a little bit of computation, it's easy to see that this minimization problem actually can be rewritten as a maximization problem that is exactly corresponding to finding the biggest eigenvalue of this matrix, the covariance matrix of the data, okay? We don't do that because that's easy and you should know it already. But what we want to emphasize a little bit more is that this is a nice first example of dictionary learning. It's a bit limited in the expressive power. Remember that now we're basically saying that we assume our data by specifying a constraint. We can see that we're actually making some assumption on the data. So we're saying we want to reconstruct the data in a way that is parsimonious, and we explain the idea of being parsimonious as asking the dictionary to be orthogonal. Here we discover that all we are trying to find is a subspace. When is that a good idea? When will it be a good idea to try to replace the data with a subspace of lower dimension? Well, when they are coming from a subspace of lower dimension. So by making this assumption, we're effectively basically saying that the data look like this. They are kind of, maybe they're, this is my best attempt to write 3-dimensional stuff. You have some big high-dimensional space, and then you're trying to look for a subspace of lower dimension. And so the data here are lying close to this sheet, which is your subspace. This is your hope, right? When you do PCA, this is your hope. We already knew it. We just now review it from the idea that we're basically saying, PCA is try to find the best subspace. This is just saying, find a dictionary which is orthonormal and describes well my data. That's it. Okay? So far, so good? This is just reviewing PCA, and it's going to be our just warm-up example. Okay. Do you like this or not? Well, computationally it's great. It's simple, and it is a great match between the analytic point of view of finding a basis and the geometric fun of finding a subspace, but yet making the assumption that the data lie exactly on a linear space might be hard, okay? So what about nonlinearity? Basically, this is going to be the rest of the examples. We're going to try to go beyond linearity. How would you do that? How would you try to go from PCA to something that is able to capture nonlinearity? Say something like this. Right, so kernel PCA, or more generally what you could do? Well, the idea could be you take the data, you map them nonlinearly in a new space, and then you find an hyperplane there. And then this in the original space gonna be some wiggly thing. Indeed, this you can do. So we're not gonna, I don't think I'm gonna dwell into this too much. Sometimes I denote the inner product like this. I try to avoid it in this class, but it's such a habit that you'll see it sometimes. Do whatever we just said in the feature space. So pick a kernel. And notice that here what you're basically doing is say, yes, I still have to pick a kernel, but then I still try to find some subset of the kernel, blah, blah, blah. Okay? So I'm still trying to learn a new dictionary based on the kernel I had. An orthonormal basis in the feature space. Now, what is the catch? There is this algorithm, we don't have much to explain. It's just you do PCA in the new space, and then in the original space it's going to be nonlinear. If you redo the calculation that we sketched here, they just look the same, okay? There is only one potential issue. What is it? From a computational perspective, PCA boils down to computing the eigenvalues and eigenvector of whom? Of this matrix. What is the size of this matrix? How big is that matrix? Enrico, how big is that matrix? The matrix of data is n by d, so you transpose that, the whole thing is d by d. So it's the dimension of the input space, okay? If you now go to the feature space, if the features are finitely many, these just become the size of the features. But if you now use kernels, well, you know that the whole idea of kernels that you might not be able to actually compute that because it might be too big. So what did we do when we were doing when we were doing supervised learning? We proved the representer theorem of some kind. We showed that there exists a way to still make these computations and get along with it, okay? Now, let's just stick to, I don't think I'm gonna prove it, but let's just stick to the linear case. Suppose that you're still in finite dimension, okay, but n is much smaller than d. Can you still compute the eigenvector of this guy in a simpler way? So if you want to compute the eigenvector of that guy, you can just diagonalize it. But suppose that I tell you that in fact this matrix here is 10 by a million, okay? The matrix x hat is 10 by a million. So if you are to diagonalize this, you actually have to store and handle a million by a million matrix. And suppose also that the other rule of the game is that you only have an eigensolver, okay? You don't have an SVD solver. You only have an eigensolver. So you can only compute eigenvalues. What could you do? Well, instead of taking x transpose x, you take x transpose. You diagonalize that. And then there is an easy relationship between the eigenvector of the smaller matrix and the bigger one, which is essentially the singular value decomposition. You see what I'm saying? I mean, you should know this. This is kind of very useful. I'm assuming, in fact, that you know it, and I'm just explaining things in a bad way. So instead of this, you now consider this. How big is this? Well, the other way around, is n by n. So this is 10 by 10 in the example. Now, if V is an eigenvector of this matrix, and sigma is an eigenvalue of this matrix, sigma square is an eigenvalue of this matrix, and if U and C is an eigenvector of this matrix, it turns out that the eigenvalues of this matrix, and these are going to be the same, at least the ones that are not 0. And the eigenvectors are going to be related. How? let's see, it should be, so this one, so let's say X transpose U is equal to sigma V, if I didn't make it wrong. Where is Ilaria? Ilaria, is this correct? What do you mean? She's laughing, so we assume it's correct. Okay? And you also have the other way around. You have XV equal sigma U. Okay, I rewrote SVD, okay? This is the SVD of a matrix. I just rewrote it in a way that is kind of more suggestive of the fact that you diagonalize this, you get an eigenvector, and then you get the other one, okay? But this is basically retelling what is an SVD. Why I'm showing you this? Well, because now I'm basically saying, if you do PCA, but you have much fewer points than dimension, you can, instead of diagonalizing this matrix, you can diagonalize this, and then use this equation to go back to the eigenvectors you want, okay? I'm not going to show you the details, but I'm leaving you as an exercise to show that if you actually have that this matrix is infinite dimensional, in the sense that you have a kernel, an infinite feature vector, but if you do have a kernel, you can still compute this one that becomes just this is the matrix that contains as entries the inner products. This is the matrix of inner products. So this is going to become if you have a kernel, it's going to become the kernel matrix. So you diagonalize the kernel matrix, and then because you just have this product of vectors, you basically get immediately a representer theorem out of here. Okay? So I'm skipping a bit this because it's really by no means the main point of this class. I'm just saying, do as an exercise, try to write down as an exercise the fact that if you have PCA with much fewer points than dimension, you can still make the computation diagonalizing the smaller of the two matrices, and then just change notation and discover that you can do everything with kernels. So aside from this computational fact, this means that we can actually somewhat implicitly do something like this by picking a kernel. And interestingly enough, if you do kernel PCA, which is a simple and yet not so widespread algorithm, there is a whole connection to another line of research basically related to the whole idea of learning a manifold through tools from differential geometry. So for those who are familiar with things like Laplacian eigenmaps or manifold learning through approximation of the Laplace-Beltrami operator on the manifold and all that line of research, you end up with objects which are essentially the same as kernel PCA or very much related from another perspective. So while the derivation is very different, kernel PCA is very similar to things like Laplacian eigenmaps and the diagonalization of the approximation of the Laplace-Beltrami operator. Okay, so we want to move on, okay? So the first example of dictionary learning is PCA. We can pimp it up a little bit and make it kernelized, and now we can do nonlinear stuff. Let's make other examples. By far the most popular example of dictionary learning, so popular that oftentimes people call dictionary learning this thing here. They say that this is the dictionary learning thing. Is basically the extension of what we saw yesterday. So yesterday we said, I remarked 50 million times, so hopefully at this point you recorded, that sparsity is a concept conditioned over a choice of a dictionary. You change the dictionary, you have sparsity on something else. So it's a completely different idea. Well, here I'm just saying, well, do the sparsity and then optimize the dictionary, learn the dictionary. So you know that you're sparse somewhere, try to find where, okay, on what. So you basically say that here you just put the L1 norm. Again, think of plugging that back up, and this is exactly what we did yesterday. And here, you're basically just saying, well, this is basically saying, just give me, here there is almost no constraint. You basically just give me any constraint, any matrix with the columns that are not too big. Notice that here the dimension of the dictionary can be much, much, much bigger than the dimension of the input space or the number of points you have. Because in some sense, we're enforcing sparsity through this. So the idea is that in some sense, we want to find a redundant dictionary, a bigger dictionary, okay? Something that has a lot of expressive power. And then in there, we want to find out the coefficients we want. So again, the representation here is the coefficients, okay? Before, the coefficients were given by the projection on the subspace. Here, I given by the coefficients over the dictionary that we now learn. Okay? So it's exactly what we did yesterday with the minimization outside over the dictionary. Now, there are a couple of questions. One is, in fact, I mean, every time I introduce an algorithm, I say that there are a couple of questions. They're always the same, so maybe you can tell me what they are at this point. What are our modeling assumptions, and what are the computations we have to do? Okay, and sometimes they also ask, what is the free parameter, when I feel particularly fun. So we're going to ask the first two questions here. The free parameters are pretty obvious here, but let's look at the modeling assumption and the computations. So computations first. If you fix the dictionary, well, then you can kind of guess what computation you have. If you're here yesterday, especially, because we discussed it for 2 hours. You just have to do an iterative software thresholding technique. Okay, this is constrained, this is not penalized. You can turn one problem into the other, okay? Or you can recycle the techniques I showed you yesterday to solve also this problem. So if you give me the dictionary and you just have to solve this for each xi, you can just do the iterative software thresholding technique, the proximal operator technique that we introduced yesterday. And notice that if I were to explain to you an extension of sparse coding where I place the L1 norm with something else, from a computational perspective, it would be all the same if I pick a structure sparsity penalty, okay? So if instead of putting L1, I put any of the penalty we described yesterday, the group lasso with overlap, from a computational perspective will be just the same, right? We do have to do this minimization here. So these slides are recycled, so this is the reason why I have some references that I've been ignoring for all the rest of the course. But they're just very spotty. But you can tell Karin that, Mickey, you can tell Karin that this is my first reference in 4 days. Okay, so you want to solve this. You're happy because you recognize that this is the kind of stuff that you know how to do. The problem is that one thing you can ask is, well, but now I have to minimize over 2 things. So if you fix psi, is this problem convex? Well, you can check that it is, okay? If you actually write it as a penalty, we discussed it for 2 hours, you can also check it that it is convex anyway. If you now if you assume that you already solved this, so this minimization is no longer here, and in place of beta I, you have the beta star I, the one that optimized that problem. Is the problem convex in psi? So you have to minimize over psi, xi minus psi beta I. There is no, this minimization is no longer there. Is this convex in psi? Yeah, why not? I mean, it's just a quadratic functional, and I have no nasty constraint on the psi. So this functional is almost nice. It is convex in psi. It is convex in all the beta i's. Bummer is that it's actually not jointly convex. So it's not convex in both variables. And this makes this problem a mess. Okay? It's a non-convex problem. In the worst case, it can be arbitrarily hard to solve. And it's an open problem to which finding, again, the only thing you can hope for is to try to find assumptions under which you might be able to solve this. Because in the worst case, you just cannot. Okay? So there is a long, ongoing effort to try to find what are the right assumptions, but in the meantime, you can also ask what are the good algorithms. If instead you ask a slightly simpler question, which is what is a simple algorithm? Well, what is the simplest algorithm you can think of if you want to solve something like this? It's convex in the betas, and it's convex on the psi. What would you do? You can do alternating minimization. The simplest thing you can do is you optimize, you fix a dictionary, you optimize over the beta i's. We know how to do it because this is just proximal methods. Then once you find the coefficients, you go on and optimize over the psi I, and you can see that it's just the least squares. It's easy. So fix a dictionary. This is just after thresholding that we introduced yesterday. Find the beta i's. Then you can rewrite the problem just as a least square problem and optimize over the psi. And if you do it, it's almost least squares. Almost, because you have this constraint on the columns that have to be small enough. So it turns out that you actually have, again, to use a proximal method, but it's easy because the constraint is just basically renormalizing. So at each step, you renormalize the column of the matrix. So you do gradient descent, and then you renormalize the column of the matrix. Okay? Again, the details are not important here. You should just think that you do a minimization over the beta, so iterative sub-thresholding, and another similar iteration to a projected gradient, essentially. Okay, and you alternate the two. I'm not saying that this is the best way of doing it. I'm just saying that this is a simple way of doing it just by alternating minimization, and it's indeed one of the main things that people are doing. And there are various variants where instead of like going all the way down to convergence at each step in the alternation, you take some steps, and then you switch to the other minimization, and you do more of a coordinate descent kind of approach instead of an alternating minimization kind of approach. Okay, but this is kind of in the same flavor. I'm not pushing this too much because I'm not claiming that this is, the best thing you can do, but this is probably the simplest thing you can do. And you can kind of see how hard it is from a computational perspective. It's not too bad. At least each iteration is not too bad. Well, I already put it there, so. So far, so much for computations. What about modeling assumptions? Okay? Think about it for 1 second. I give you, say, a bunch of vectors, and suppose that I tell you that they are, while you look at them and you see that they are 100-dimensional, in fact, they only have the first 3 entries different from 0. All these vectors have only the first 3 entries different from 0. Where do they live? They don't live in the full 100-dimensional space, but they will lie where? On a subspace spanned by the first 3 coordinates. Right? It's a linear subspace. Why not? And it's just spanned by the first 3 coordinates. Now I give you another set, which is now have the second 3 coordinates. Where does it live? So now you have 2 subspaces, each one of dimension equal to the sparsity level. If the sparsity is 3, you have 1 subspace of dimension 3, another subspace of dimension 3. So if I give you signals of dimension d, and I tell you that the sparsity of each signal is this, what is the biggest set they can lie on? Can they lie in the full space? No, right? Because each of them is sparse. But where do they live? The set of all vectors that are size d, but they're sparse s, is going to lie where? It's written here. Each one lie on a subspace of dimension s. You have how many subspaces of dimension s in a space of dimension d? You have d choose s subspaces. And all the possible data are going to just live on the union of this. Okay? So when you're doing sparse coding, you're assuming that the data lie on this tessellation of subspaces, each one of dimension equal to the sparsity level, and at most d choose s. Notice that here and this is a comment actually, so in everything I discussed so far, I always assume that things are linear passing through the origin, okay? We don't put the offset. And the only reason why we did that is because it's very easy to put the offset. Either because you add just one term in the gradient, or because you can even do it in closed form. So If you now allow yourself to not have subspaces pathing to your origin, you can basically see that you're assuming that your data can lie on some tessellation of the space as a collection of subspaces. At most, D choose S, which is quite large, but it's going to be like union of, if you want, piecewise linear pieces. Okay? So if you want, this is pushing PCA from something linear to many, many linear spaces, each one of dimension S. This is the assumption underlying sparse coding. Also notice that the way you compute each subspace depends on the way you compute all the others. All these minimization problems are coupled among them, okay? The way you choose this D depends on all the data, depends on all the points. So sparse coding solves a global problem to, in some sense, find an approximation of this set of subspaces. Okay? So we had PCA, then we bend the PCA, then we move from essentially an L2-like regularization to an L1 regularization, and then we do get the collection of linear subspaces. What about k-means? So k-means is usually seen as a way to do clustering. But it's perhaps even more famous as a way to do vector quantization. What do you mean? You have a bunch of vectors, and you want to replace those vectors with a set of vectors that are going to be binary vectors with only one entry different from 0. More generally, some entries different from 0. So you want to quantize the vector, okay? You want to binarize it in some way. Here we're going to binarize in an extreme way because we're just going to keep one entry different from 0, and everything else will be exactly 0. So k-means is doing exactly this. How? Well, you can just take the dictionary learning perspective, and you say that the matrix D, the dictionary, is anything. You don't put any constraint. On the other hand, you make a huge assumption about the set of coefficients. So far, we assume that the set of coefficients is continuous, okay? We assume that, you can choose it amongst a collection, a continuous collection of coefficients. Here, we actually assume that you have exactly k coefficients. And these k coefficients are the element of the orthonormal basis in Rk. Or in other words, the first coefficient is 1, 0, 0, 0. The second coefficient is 0, 1, 0, 0, 0, and so on and so forth. Okay? So each of the coefficients, the vector of coefficients, is extremely sparse. It has at most one entry different from 0. So we claim that this is exactly what k-means does. So we now have the minimization over the linear part, and then the beta I. Beta I here, remember, is a vector, and is just one of these super sparse vectors. If you can refrain from using your cell phone, at least in the third and second line, it helps me concentrate when I speak. Thank you. So this is just PCA. This is just k-means. See, it's your fault and your fault. So let's see what it does, okay? So exactly the same story as before. I want to know what are the computations and what are the modeling assumptions. Turn out that as computations, I'm going to do, again, the naive thing, which is alternating minimization. Just is going to discover that this is what people call Lloyd Algorithm. So we fix the dictionary, and then we have to solve this. Well, but what is this? We're just saying that for this you can see as an assignment step. Because what you're doing is basically saying, I have a matrix, okay, psi. And now I'm going to assign to each point a column of the matrix. When you multiply a matrix by an element of the orthonormal basis, you're just selecting a column, right? So when you do this, you're basically just saying, find the column of the matrix which is giving the best reconstruction, or if you want, which is closer to the point I want. So you're selecting a column. When you solve this minimization problem, you're just selecting a column. Correct? That's it. This is the first step of the alternative minimization. Given a dictionary, for each input point, find the column closer to that point. Do you agree? Now you have the second step. You now found all the vectors that are close to certain columns. So you now have that, of course, more than one vector can be close to the same column. Here we are assuming that k, the size of the dictionary, is typically smaller than the number of points. So you will have the two vectors go to the same column. So if you now call Vj the set of vectors that go to the same column, you can view that as a partition of the space. You can now view everything we've done so far as follows. You have the space of the input, throw a bunch of vectors. What are these bunch of vectors that you throw at the beginning, to initialize with? They're just they're the centers, but what are the centers in here? The points that you use that you assign each input point to are just the column of the matrix. So by choosing a dictionary in k-means terms, in clustering terms, is choosing a bunch of centers at random. Here I'm choosing a bunch of columns at random, which are just the element of the dictionary, okay? Then I assign each point to the centers. That is, I find the column of the dictionary matrix closer to each input point. And if you want, by doing this, I now made a partition of the full space in regions that are described by one center or one column of my dictionary matrix. And this is somewhat the clustering perspective of k-means, collecting together all the points that are close to the same column of the dictionary. And this is the first step. Now we have to do the last step of the alternative minimization, which is optimizing again over the dictionary. Okay? So we have to take this thing here, where now psi is the minimizer of this, and minimize over the remaining variable, which is, sorry, phi is the minimization of this, and we still have to minimize over psi. If you see, these points, as we said, are going to be partitioned in this set Vj, okay? You can partition them, and you can rewrite this sum, which is over all points, as the sum over all the partition, and then the sum over the element of each partition. And you can now check that if you're minimizing over the columns of this matrix, this minimization decouple. Instead of minimizing over the matrix, you just minimize over the first columns, then over the second columns, and so on. And you minimize over the first column in the first region, over the second column, over the second region, and so on and so forth. And if you look at this, if you stare at this just a little bit, you can convince yourself this is just computing the mean of the point in the region. Because if you take the derivative of this with respect to aj, you get twice x minus aj. You just put it on the other side of the equality, and you are just computing the mean. So the optimizer of this is the mean of each set. Which basically means if you do alternating minimization on this vector quantization problem, the first thing you do is you find the closest coefficients that you can interpret as an assignment step with respect to randomly assigned centers, and then you do an update, which is the update of the centers, okay? This is the usual Lloyd algorithm. This is what you call the Lloyd algorithm. It doesn't come with the guarantees to solving the problem efficiently or exactly, but it's a reasonable greedy procedure, and it's just alternating minimization. So particularly because it's alternating minimization, what you know is that you're not going to increase the objective function, okay? So this algorithm is going to decrease the objective function. Not only that, how many possible solutions you have here? A ton, but not infinitely many. This is just a combinatorial problem. So at some point it's going to stop. Either you stop it before, because it might take a while, or it's going to stop. It's going to stop where? Well, somewhere in a local minimum, most likely, okay? If you're lucky, it's just going to be in a local minimum. You have no way to, up to now, you have no way to hope that this is actually a good minimum, okay? Or a global minimum, but it's a local minimum. So from a computational perspective, alternating minimization, it's easy and actually gives you back some interpretation. The interpretation in terms of assignment and update of the centers, okay? Initialization is choosing centers at random. Minimization of the coefficient is assignment. Minimization of the dictionary is update of the centers. It's just an interpretation, okay? Matching the one we already know. And along the way, we see where the clustering is coming from. It comes from getting all the coefficients with vectors, input vectors with the same coefficients. Blop. Oh, beep. We already said everything. How many of you know k-means plus plus? So k-means plus plus is a kind of nice result because it says essentially that while there is no deterministic algorithm that can solve k-means in, with global guarantees, there are actually randomized versions that can approximately solve the problem. That is, getting with high probability or in expectation close to the global minimizer. In fact, the result is even stronger than this. It gives you an initialization, which is itself, by nothing else, an approximate global minimizer, close to the global minimizer of the k-means functional. Okay? So the k-means is just an initialization, and the initialization alone is in expectation, it's a random initialization, and in expectation is close to the global minimum of k-means. So this is good news because it's, of course, these things are hidden in the fact that it's stochastic. So how does this initialization works? Well, you tell me, if you have to do an initialization of something like k-means, and instead of doing it randomly, you just want to do something that seems to make a bit more sense, what would you do? Well, suppose that you have this stuff, okay? You see that the big problem might be when you start to put two centers inside of a cluster, for example. If you have if you put centers very close to each other, that might be, one problem, okay? Because you're going in and splitting things up. Because the moment you pick the centers, you have to sweat a lot before you decide that actually the 2 points can be this and, can be put together in just one single cluster. So one idea could be, well, let's try to take an initialization and spread out the points nicely. So one way to do it is to say, okay, first I pick 1 point at random. That's it. Okay? Then I pick the second point so that in a probabilistic way, in such a way that with high probability is going to be far away from the first point. How do you do that? Well, for the remaining points, you compute the distance to the point you already picked. And then you take a probability that is somewhat proportional to the distance. So if the point is very far away, it's more likely to be sampled. If a point is close, it's less likely to be sampled. That's it. It's kind of an important sampling technique based on the distances. And you keep on going. So it's probabilistic because the deterministic version could be take a point and take the furthest away. And then take the furthest away from the two. Here you're saying, take a point, take with high most likely take the point that is furthest away. And then you keep on going, and you repeat. And then you stop after k steps. And you get centers, okay? And it turns out that these centers are epsilon close to, in expectation, to a global minimizer of k-means. Now you can ask yourself, can it do better than this? You're already quite happy, okay? Because this is a hard non-convex problem that you can get reasonably close to a global solution. Of course, you can also ask, what would you do typically? Well, you would rerun Lloyd algorithm, I guess. You have an initialization, and you use it in initialization. You have a random selection of points, and you use an initialization. Can Lloyd algorithm hurt you? Well, we just said it's an alternating minimization algorithm. So if you start from initialization, it can only get better. So the typical way you do this is that you actually do a few initialization, a few Lloyd algorithm, and then you pick the best solution, because you know that everything is random. Each of these solvers is quick, so you can allow yourself a few usually, because you basically just have to compute distances among all the points, which is big but not horrible, and then you're good to go. Okay? So k-means is nice because from a computational perspective allows to solve the problem reasonably easy with initialization with some global guarantees. What about computations? Modeling. Well, if you have to do the analogy with sparse coding, the analogy is quite obvious because in some sense, from one perspective, because k-means provides you a sparse solution, very sparse. Because we said that each point is associated with a coefficient vector. And how does the coefficient vector look like? It has only one entry different from 0, and that one entry is actually equal to 1. So it's a super sparse representation. When you reconstruct, each point is going to be replaced by whom? By the closest center after the minimization, okay? So this means that when you approximate this thing, it's very similar to what? Quantization, but if you say you have a function, okay? You're basically dividing the domain of the function in sets, and then in each of these in intervals, and then in each interval you take a constant, okay? Here, rather than a constant, you take a vector, the center of mass. But it's very similar to a piecewise constant approximation of the set of points. Imagine it as a surface, as a circle. You basically replace the circle with a set of points. So in that sense, it's a multidimensional, is the equivalent of a piecewise constant function approximation technique in the case of a multi-valued function. So if you have a function that rather than one value has many values, in this case, it's just the vectors themselves, then you replace this function with just one vector, okay? All values are just replaced with one vector. So this is the quantization point of view. This is the sparse coding perspective on k-means. And if you want, this is also giving you the idea that from a reconstruction perspective, you're assuming the data to like close or be well approximated by this kind of piecewise constant things, okay? Notice that this is a bit different from the usual clustering perspective. There's nothing here that says, well, if there are clusters, it's going to be better. Sure, it's kind of that, but you can also think that you really have a curve, and this curve, you can just interpret having clusters not to be something that is well separated by something that is, in some sense, piecewise constant. It's just another interpretation. Now, if you have this interpretation in mind, you kind of feel obliged to ask the further question. It is like, why piecewise constant? Can I do piecewise linear? Why should you do piecewise constant? Can you do something higher order? In some sense, that's what sparse coding was doing, right? It was dividing the space in regions, and each region actually had a full linear space assigned to it. So can we do the same thing here? And the answer is yes. And it's basically what is called k-flats. I like k-flats because it's a relatively simple and then cute idea. I tell you a wrong version of doing k-flats that gives you an idea of what it does, okay? Suppose that you do k-means. You have done k-means. You divided the space in regions, and then you say, well, instead of actually computing the centers, I do PCA inside of each region, okay? This is one thing you could do, which means that the region are computed by checking the distance to just a vector, but then in the end of the day, you approximate the points with a concatenation of subspaces, with these flats, all right? K-flats is almost doing this, but it's doing it in a better way. What you should be hoping for when you do k-flats is if it's really a generalization of k-means, that rather than piecewise constant or piecewise linear, you would like to change what I just said. How? But what I just said is do k-means, partition the space first, and then do PCA on the partitions. Well, this is not a generalization of k-means, right? It's k-means plus PCA, local PCA. So what we would like to do, if you really want to take seriously the extension of from piecewise constant to piecewise linear, is to replace the center computation in k-means with a flat, with a PCA-like computation. So what you would like to do is to, instead of picking a bunch of centers at random, pick a bunch of subspaces, for a PCA vector at random. Assign the point to the closest subspace, and then recompute the subspaces. So you want to throw in about 3 lines, assign each point to the line, and then, once you have a partitioner of the space, recompute the line. So you literally replace in the center, you replace centers with collection of vectors that you view as spanning some subspace, and center updates with a PCA computation. What is the difference? Suppose, for example, that you have, I guess one example is the cylinder. Suppose that you have a cylinder, okay? If you do k-means, it's just going to create, tessellate all the side of the cylinder with spots. And then in each spot, you put a PCA if you do this k-means plus PCA thing. If instead you allow yourself to create partition using flats, the regions are going to be how? Well, in k-means, you have the cylinder, and then you just take centers and points close to the centers. Here, what you're hoping for is that you slice it up, essentially, because you put if this is your cylinder, you're going to put a flat like this, and so all these points are going to be close to the same flat. So in some sense, the cluster, the region you create, is going to be this whole stripe running through the cylinder. So in that sense, k-flat is more global, because if there are points far away that are close to the same hyperspace, they're going to fall in the same cluster. Whereas k-means is just going to put them far away because they cannot be close to the same center. So k-flat is more global. I'm not going to discuss computation. I'm going to skip them because they're the same of k-means, literally replacing the mean computation with the PCA. And that's it. And the bad news is that we don't have k-flats plus plus. We don't have a nice initialization that gets close to the global minimum. So as far as I know, we are just stuck with local minima. Let's look instead a bit more, again, at the modeling point of view. You're now doing some form of representation. Is it sparse or not? So in k-means, you were assigning each point to a vector, and then you were outputting the representation vector with 1 and then all zeros. What about k-flats? What do you do? Say it again? You have this psi1, psi2, psi3. Each of these one is an orthonormal basis of that subspace. So as he just said, you have a collection of subspaces. Each one has an orthonormal basis because it's a PCA. First of all, you assign the point to a subspace, and then you compute the coefficient in that subspace. So by assigning the point to that subspace, you decide who's 0. But then this C2, if you want, is a bit misleading. Psi2 is not one vector, it's many vector. And C2 is the projection on those many vectors. So it is sparse, but in kind of a structured way. A bunch of coefficients will be different from 0. And what are these coefficients? Well, they have a geometric meaning. All the things that are close in one region, or if you want, they're well approximated by the same set of vectors, will have coefficient different from 0. So it's a form of sparse representation with a geometric flavor. So from a reconstruction perspective, from a representation perspective, we're assuming that we're doing a structured sparse representation with structure defined by geometry. From a reconstruction perspective, as promised, we go from piecewise constant to piecewise linear. What is the difference with respect to sparse coding? Also, sparse coding was a collection of linear pieces, right? What is the difference here? If you fix k, not much from a modeling perspective. But if you now allow yourself to let k grows, k is a free parameter, so you can let it grow. Basically, what you have is that the number of flats increases. And if you want, for those of you who are familiar with manifolds, you remember a bit how you approximate a manifold with tangent spaces. So you grow more and more tangent spaces around the manifold, and you make a finer, finer approximation. Whereas this you could have done in sparse coding only by changing the sparsity level, and not even that, because it's slightly different. You have to, in some sense, the number of flats, the number of subspaces in sparse coding is d choose s. So the only slack you have is in S, but anyway, you cannot approximate, you cannot be arbitrarily precise in approximating a surface like that, okay? So they're similar, but they're different. So, let me just mention quickly, because this is also nice, and we can go and say to Mauro that I always mention him, I always advertise him, so he should always thank me. Another way of doing something similar to k-flats. So k-flats is basically saying, I want to optimize and get the best partition, okay? And so I do it, the best partition is like the one that is best approximated by linear subspaces. Another idea is that of saying, instead of optimizing, let's take a big family of partitions that are coarse to fine. It's a tree of partitions. The first partition doesn't have many elements, and each region is pretty large. And then I split each region coarser, coarser, finer, finer, and finer, finer. So I have a tree at each floor of the tree. I have a partition, and it gets smaller and smaller. And then what you do is that you basically start to do recursively PCA in each partition. And then if your PCA in a partition doesn't give you reconstruction good enough, you further split and do PCA again in the lower partition. If your partition is good, say you have something that is like flat here and then goes like this, and you're lucky and you manage to split it nicely, okay? Here, one PCA will be enough. Here you see that if you do a PCA, you get all this part, so you split again, you do another PCA and do another PCA, and eventually do enough PCA to perhaps control this. So in some sense, you give up finding the partition, optimizing over partition, and you just look over partitions, okay? You select over a predefined family of partition, but the thing you gain is that you can do it in a coarse to fine way. So suppose that you get into a region and say, well, no, this partition is not good enough. I want to refine it. That's easy. You just go down one level. What do you have to do if you do the same thing with k-flats? Well, it means that you have to add one cluster, you have to add one flat. So you have to do from k-flat to k+1 flat. And how do you do it? Well, you kind of suck it up and you have to do it again, from scratch. There is no obvious way to initialize k-flats. So in some sense, k-flats is more ambitious. It solves a non-convex optimization problem. And in principle, if you can solve this non-convex optimization problem, it could give you more juice, because you could find the great partition of the data. Something like this starts not optimizing the partition, but just building this family of partitions. It doesn't optimize, and so in principle, it can be suboptimal. But it allows yourself for this kind of multi-scale approach, where you start coarse, and then you go finer and finer. And in some sense, my feeling is that depending on the kind of scenario you are, especially when you are in a large-scale scenario, the multi-scale approach can be a very interesting features. Possibly paying a bit in terms of accuracy of your model. And sometimes when you have very high dimensional complex data, it's not always true. I mean, having the right model that is very hard to compute sometimes pays off, but sometimes having a simpler model that maybe is a bit worse, but it's easier to compute and to explore, might pay off. So this is kind of my prejudice about all models I see. And this, I think, maybe it's what's going on here when you compare these two approaches. Okay, so I'm done. So just one comment. So before you start to read everything, let's summarize the things before. So the idea was to introduce this idea of learning a dictionary, a general framework to do it, and then show you how several algorithms that in fact you already know probably can be just rewritten as special cases. And in doing this, we get some feeling of the various alternatives we have for learning a dictionary. Linear spaces, non-linear subspaces, union of subspaces, and essentially manifolds through piecewise constant or piecewise linear approximations. And by the way, I didn't mention it, but one thing that one could obviously try to do is, in some sense, there is an asymmetry here because we do k-means, and then we do k-flats. And then when we do these multi-scale things, we just do it linear. But in fact, an obvious thing is, can you do something like a multi-scale k-means? Can you do it, can you do something like this with piecewise constant rather than PCA? And that's basically what Enrico has been doing the last few months. And the answer is yes. And in some sense, you have a nice parallel between k-means, the optimized one, and the one with multiple scales, and k-flats, and well, I guess the linear one, Mauro calls it geometric multi-resolution analysis, okay? This scaling stuff. The last thing is just a quick comment. Matrix factorization is the generally problem of I give you a matrix, split it in a bunch of other matrices, okay? That's what it is. I give you a matrix X, split it maybe in two or more factors. Now what we do when you do dictionary learning is this, and you can ask, well, is this related or not to matrix factorization? Is there a relationship? And basically the point here is that this minimization, if these minimizations are really one independent to the other, you can take it outside, right? So every dictionary learning method can be seen as a minimization over the psi and the beta simultaneously. And then I can write it like this if the minimization problems are independent one to the other. So in this sense, dictionary learning is just a special case of matrix factorization. In the special case where you have a matrix factorization problem like this, where you optimize the matrix B, but independently over each column, okay? So if you want, dictionary learning is just the way I phrase it here, is just a special case of matrix factorization. So if you want, when you look at a matrix factorization like this, is an even more general form of dictionary learning, where what you could do is to find the dictionary, but then find coefficients, trying to to couple the way you find the coefficients for all the different points at once. Here, the coefficients are only coupled to the psi. So the only global optimization in this form is over the psi, whereas the beta, it's local. Whereas here, you could try to do both at the same time. Okay? So I'm going to skip completely the similarity preservation, and maybe I'm just going to show you quickly when we restart. So what we want to do right now is literally introducing the idea of unsupervised learning of a dictionary and go through a few examples, trying to emphasize both the kind of computation that are entailed, discovering that most of the time we have to struggle with non-convex problems, and then getting an idea of what are the modeling assumptions, where the leading idea is that in some sense, data are a collection of things, signals that lie on some region that has some regularity and is possibly like a complicated nonlinear region affected by some noise, okay? All right, so let's take a break and be back in maybe 25 minutes and we can go home.